How you guys doing today?
Good, how are you?
Good. So, I hope you guys all have had a really good spring break. But this is the one today. So, you guys remember what we talked on Wednesday? We talked about the stability of carbocation. So we talked about if it's a higher in order, small substitute is more stable. So you can say this one is maybe the most stable form of your carbocation. See the partial charge in this carbon here. Second is the secondary carbocation. The primary. And the least one would be just the kind of a metric carbocation. So there's no R groups on it. Okay. So we talked about this is the most stable form of a carbocation, but once again, carbocation is not stable. We're just doing this by relative term. They're all unstable, but among those four possible forms for your carbocation, this might be the best one and the stability wise. Okay. And we talked about the hyperconjugation. And we also talked about the inductive effects that explains why it's so much more stable than the other three. Okay, so you can also double check if you missed the YouTube video, but yeah. So this is what we left before. Okay, and let's try to use how they work in the actual reaction mechanism. So if that is the case, okay, let's try to do something over here. So if we have some energy diagram over one of the directions we talked in this chapter, maybe you can try to give you one example here. We try to do it with the HBr from hydrobromic acid here. And then once again, you're seeing this one will go up to, they need to go up the activation energy to proceed, right? And then they're going to have some reaction intermediate. Or you can say just intermediate sometimes, but it's okay. And then you have to go another puddle over here. Okay. So overall, this will be more stable in the product side when you become product. So this is your reactant solution. And then obviously this is a negative. So it'll be so if you do this one, this will happen spontaneously, but they need to go over this puddle here. This is what we call. So just the same as schizophrenia symbol, but with the double dagger symbol on the right top corner as activation. You guys remember this, right? We talked this before. Just a quick review. I'm going to explain why is it matter in here. Okay, the carbocation stability. So once these two is your first transition state. Okay, this is the second transition state. It's simply because before they get into the intermediate or the product, there is some like a semi in the middle type of process, semi-process the reactants to the product type of state is what we call transition state. Obviously, this transition state will be very unstable because they were in the somewhere in the right in the middle of the reactions, where that will be the time they will experience the most of discomfort. So this is energy diagram-wise very high point on your reaction diagram. So if that happens over here, this is what you can see as your intermediate is where you can find the carbocation. So what happens to this one here? You see this the pair of electrons in the p or the pi electrons are going to find something that is positive. So that will be hydrogen on here, and then this will the pair of electron in here will goes to the bromine. So they will grab either on this carbon or this carbon. Okay. So let's try to do two possible scenarios. So if they get in on here, there is one. Okay. So this is where you can have. Let's try to do this one first. Okay. So you try to put the hydrogen on this carbon here. Okay. So you're making this type of intermediate here. And then another thing is you can put the hydrogen on here. Okay. So you can have. Here. So now the two possible scenario. This is it now here and here, here and here. Okay, makes sense, right? So then, if you look at this one over here, based on what we just discussed for the stability of carbocation, this carbon that has positive charge, it only has one carbon right next to it. So this is the primary carbocation, right? This is a primary carbocation. But this one, it has 1, 2, 3 R groups there, right? So this is tertiary. So which one will be more stable between these two? It will be this one, right? Okay. So in that case, you're going to have a more stable carbocation form. That will be once again lower in energy. So if they go in this way. If you choose this one, they can go this way. Because your reaction intermediate form will be in lower energy. So that makes your activation energies also become lower with it. So this reaction will go much slower. Does it make sense? So your reaction intermediate here, right? But if it's the more stable than the other, it will be in here. And that makes much lower huddle. Does it make sense? Good. So then this one will prefer to have this one. And this is why, this is where you're gonna have later in the second transition, bromine and to here and makes the final product. I hope that makes sense. It's okay. So they because it's more stable and that carbocation form than this one, they will have a later on this type of intermediate, and that is why later this bromine anion will attack this carbocation looking for something positive as a nucleophile, and they will get to here, and this is your product. So if that makes sense, I'm gonna go over one more thing, okay? So to here. So whenever you have a reaction, looks like this. So this will be much higher in the product position and energy diagram wise, right? So this is positive. Okay. So this is what? In the conic rays. Okay. So if you have this type of reaction over here, there's one rule I want you to remember. This is what we call Hammond postulate rule. Okay. So what I mean by that is this is once again is your transition state. Okay. So if it's your transition state, and energy diagram wise, your product energy level and your transition energy level is closer than the one on the rectangles. See, these 2 points is not so much different here, but here and here is big gap there. Okay, so in that case, energetically state speaking, we can say this transition state form and the product should share similar structure. Okay, but the transition state is so different from the reactants that most likely the form of these two, structure of these two, won't be so similar to each other. So we call this Hammond postulate. So you have either exergonic, endergonic reactions. You're going to see the energy level of transition state is either close to product or the reactants. And then it is the one that close to product or reactants, that those two are close to each other, should be having the similar structure, similar form of to each other. Because energetically speaking, it's very similar in the position wise. Make sense? Does it make sense? Okay. For example, the first step, what we just did. Okay. Transition state is this one. You had a double bond is going missing and going to hydrogen, and it was going to be here. Okay. So obviously, this is not so similar to the reactants anymore because you're missing double bond over here. So it'd be single bond, or it's almost single bond now, like half double bond, half single, somewhere in the between. And there's a semi bond here, and this is going to be up to here. So in this case, whenever you have a carbocation form and have a attachment on this hydrogen here, okay? And then these two are more similar to each other than this one, which is double bond. So as you can see, they're not so similar to each other anymore, but to the intermediate here. So in this case, it'll be intermediate in this chapter, okay, in this part. So that kind of explains the Hammond postulate that if it's in the closer to each other in the energy diagram, they might have a similar form or structure together. Okay? But maybe not so from the other one that is far away from in the diagram. Makes sense, right? Is it some? Okay. So then the second step was this one, right? Second step was this one. Okay. So you have an intermediate, and you have a second transition. Here is your final product. Or you can say any other exergonic reaction here, which will be reactance or transition and product. In this case, these two are close to each other, right? In this diagram wise. And then these two will be resemble to each other. Okay. Also following the Heyman postulate. Okay. So in this case, in the second step, what we just did should be also similar to what you had in transition state over here, right? So be this one. Okay. And they're doing now this in just this transition here, and then this is just the so these two now will be resemble each other in the product. It's just not so similar in the form anymore. Okay. So it's a very simple rule actually. Whenever you have exergonic endergonic reactions, you're going to see the energy level of your reactants and transition state and the product will be somewhere in the closer or the not far away from each other. Then the ones in the close to each other is the one that resemble in the form or structure wise, following this Heyman postulate. Kind of makes sense. Kind of. Can I move on? Okay, so let me give you just the example here. So if I give you this type of energy diagram, okay, transition state should resemble which one? Is it reactants or products? Perfect. That's it. That's what I've been actually telling. But I just want to show you more specific example. But technically, I mean, it kind of makes sense though, right? I mean, if you have some two other compounds in the so different energy level, they should have a less chance to be resembled to each other, obviously. But when you look at this reactions over the energy diagram, it also kind of explains it in the mechanism wise. All right, so just a couple more things. So if you have this one okay, over here, maybe can you guys look at this one, and then you need to look at this one as okay. You guys need to see this. So on the exam, I'm not gonna do this one. I'll just do this. But you know now it's this, right? Okay. So I'm not gonna explain. But if you have this one here, so this is what we did with the Markov-Nikov rule. Once again, because of the higher stability of the carbocation position, this will bound to. So here's the thing. If you have this one let's go to here, right? But the problem here now is either going to put this one here or here, right? So what do you think? It will be going to be here or here. What do you guys think? Which position will be the more stable carbocation? Here or here?
The first one.
First one. Because it's more substitute right here. This one has only one, right? 1, 2 hydrogen. This 1, 2, and there's 1 hydrogen. So this position will be more stable, right? So this one, okay? So this one over here. And just I'll treat a little bit more, but the thing is, this is a secondary, but there's a potentially what? Even higher stability because tertiary position, if you can. So what they do is, when they got this one here, there is another hydrogen implied here, right? You see that here, and they move So they makes more stable carbocation form. So they just moving the hydrogen with the pair of electron together here. So we call this the hydride seat. They do that because they want to make an even more stable carbocation. Because this is the position where you can have a tertiary carbocation. So the hydrogen here now is moved to there. You see this hydrogen and electron pair, whole thing moves there. So the plus charge now moved to here. And then this one will go there. Okay. So you have actually another, it's this one. There's a even more extreme change. Does it make sense? So they change the position of the carbocation by just shifting the hydride. Means the hydrogen with the pair of electron just, and then it goes to the even more stable position for the carbocation, and then they do the second step, which is your chlorine comes in to attack your electrophile. So does it make sense? So not only this one. So if I give you this, and if you do this one will be really wrong, because it can't be. In any case, it can't be this one. But this one is better. But also you can think about there might be even better position in here. Then you might have to consider there might be a hydride seat, so they can be more stabilized. So that makes the products over there. Okay. Okay. So I'll give you just one more.
Will you say the name of the rule again?
Which one? This one? It's Markovnikov. Markovnikov.
Can you spell that?
Yeah. So Markovnikov. I think it's the, I'm not sure it's the Russian name, but Markovnikov. So this is the way you can have a carbocation in the more substitute carbon position. So it will be more stable. That's why. Makes sense, right? So just one more. So you have this one. Okay. This one. Okay. And this is here. And then in this case, you also can think of here, not here. I'm not going to put the chlorine here, but here, because so this is where you're going to have a potentially carbocation position here, right? So, right? This is the one product you can do, but the okay.
Where's the double bond at then? Where did the double bond do it?
Here. So the double bond is used to grab this one over here. See the one pair of electron in here. I'll grab this one and goes there. Do you see it?
Not really.
Not really. So okay. So the pair of electron on the pi bonds, they relatively can be more easily accessible for those to use to make a new bond. So that means they break the double bond here, and they grab the one of that is something that is more nucleus wide, like a positive, which is a hydrogen is perfect target. And then the electron density all goes to the chlorine because it's more electronegative.
Gotcha.
Okay, so then this will become negative charge, which is what? Your next step of the nuclear file. So then once they have found the positive position, they will attack, which is your carbocation position. So that's why you have a. All right. So All right, then you have also another one that you can do is the what we call what we call metal sheet. Means actually not just the hydrogen with the low pair electron, but these two move there too. So that makes the this addition as well on this position as well. Okay. So I think this exceptional case, I don't think I'll put on the exam, but I still want you to know there might be the possible scenario that they may do with the hydride shift, metal shift, because the carbocation stability issue there. But I really don't think I'll put this on the exam because it's too tricky. But please put this in your mind. So in case you may have to know how you think about this. Okay. All right. So does it make sense? We good? Do you have any question about anything? No, we good. Okay. All right, good. So then, so that's it for the chapter 7. Chapter 8. We're gonna learn about the some alkene related reactions. So you're gonna learn about the hydration, hydrogenation, and you're gonna also learn about the bromination, or in overall we can say halogenation because we're gonna put bromines and chlorines and fluorines on those alkene groups. So you're actually going to see lots of oxidation and reduction on your alkene compound. So this is a quick overview of the chapter 8. There's one thing I want to tell you is from the chapter 8, you're going to have a summary of the reaction on the very last 2 pages of your each chapter. And then I'm not gonna lie, if you just memorize this one, you will have a very good chance to do well in exam 2. So it costs a lot. It takes us quite a bit of memorization process. But I just want to give you one tip already. We save a lot of time until the exam 2. But from chapter 8, you will start seeing end of the year each chapter in your textbook. You see the summary of the reactions. There's a lot of them, maybe I think 10 or 15 in every chapter. You may want to just start memorizing them from today. Okay? So this will be really helpful for your exam problem solving, because whenever I go over each reactions in the chapters, what I'm normally doing is I'm gonna go over all the mechanism, detailed process, how it happens. But technically speaking, to be honest with you, all you need to know is what goes in and what product will be made. That's all, which is just this one. So if you just go ahead, try to look at from the summary every time you're going to study reactions in each chapter. This will be very helpful even from today. We still have a lot of time, but just keep this in your mind every time you go into the chapter, from chapter 8 all the way until the end of the semester. Just try to look at the summary and try to memorize them. And that will be really helpful for your exam preparations. Okay. Make sense, right? Okay. So once again, the key point here is you don't have to know about the mechanism, how it happens, how does the electron moves, how does the product becomes more stable and everything. But what reactants will make with what catalyst make what product, that's the only thing you have to know is all here. So this will be really helpful. Alrighty, so I'll just stop here today, okay?